Morning, AP Chem. Welcome back to learning. A little bit different learning than we're used to, but you still got Mr. Coker explaining AP Chem. And this week we are going to cover Chapter 16, Solubility and Complex Equilibria. This is the KSP information that we kind of started talking about before the break. We've covered the Ka, the Kb, and all of the general equilibrium stuff. This follows the same rules. My plan is for Monday this week to cover 16.1, which is the basic KSP stuff. And then 16.2, I will post a video for that tomorrow. And that's going to cover precipitation and qualitative analysis. And then 16.3, I'll post a video on Wednesday. What I'd like you to do is watch the videos and try sample problems from the chapter, from the back of the book, or back of the chapter rather. And then I'd like you to go ahead and do the multiple choice practice for the AP test that we always do, and send those to me. I will correct them. I will not grade them. We're not grading anything this week, but we're still covering Chapter 16, so go ahead and do them. Don't worry about if you happen to make a few mistakes, but just do them to the best of your ability. I will correct them, get them back to you so you can look at what you missed. And then I will send you a quiz. The quiz is not for points, but the quiz is just an excellent chance to try out what you know from Chapter 16. So I will be sending you a quiz Friday to try and send me back the answers. So these will all be posted to the Google Classroom. I am going to attempt to use Google Classroom. Please let me know if I'm doing it right. If the stuff that I'm posting to Google Classroom is coming to you in a usable form that you can get to and see and do. These videos for each of the sections of Chapter 16 and moving forward, any more lectures that I need to do before we're able to be back in person with each other, I will be posting, of course, to my YouTube channel. So make sure you check those out on the YouTube channel. So without further ado, let's go back through what we've already begun discussing about solubility equilibria and the solubility product. So remember that all of this deals with saturated solutions. You do not have solubility equilibria if you are in an unsaturated solution. Solubility equilibria implies that a solid, ionic solid, some people call it a salt. That's kind of a synonymous term for an ionic solid. The technical definition of salt is that it is a product of an acid-base reaction. But as you know, salt and water are two products of an acid-base reaction, and a salt is a positive and negative ion combination. So you can kind of think of it like an ionic solid. But when a salt is unsaturated, it is not considered an equilibrium. You do not have the recrystallization occurring. But in a saturated solution, when you have solid sitting on the bottom and you have dissolved all you can of the ions in the water, you will have not an end to the reaction, but rather a dissolving and recrystallizing at the same rate situation. And because it is a forward and reverse rate happening at the same rate in both directions, we consider it to be an equilibrium, and it obeys all the rules of equilibrium that you've already learned and probably will need to review before the AP test, but hopefully this will be part of your review, is continuing on with this discussion of the solubility product constant. So just to kind of get you oriented here, let's say that we have the situation in the bottom left, calcium fluoride dissolving in water. Kind of appropriate here to pick calcium fluoride. The mineral on the bottom right is the purple color of calcium fluoride. It is the state mineral of Illinois. It's often found mixed with limestone. Calcium fluoride is CaF2. Writing its dissolving equation would be CaF2 solid makes Ca plus 2 plus 2F minus. So if we write KSP expression for this when it's at its equilibrium point, in other words, when it's in a saturated solution with some solid on the bottom dissolving and recrystallizing, KSP for this would be the concentration of the calcium plus 2 ion at equilibrium times the concentration of the F minus ion at equilibrium squared. The solid is not included, it's a solid. So as long as you have solid in contact with the solution, the amount of the solid would be immaterial. You could have just a small little crystal of the calcium fluoride dissolving and recrystallizing, or if you added filled the whole bottom of the beaker with calcium fluoride, it would not make any difference in the amount of calcium and fluoride that will dissolve. More just means more surface area, but whatever that surface area is, there will be dissolving and recrystallizing across that entire surface area. So it doesn't matter how much is sitting on bottom. You can't add more calcium fluoride solid and expect this equilibrium to shift to the right. Chatelier's principle may make you think so, but it won't happen because the solid is not part of the equilibrium. So just remember, the amount of solid doesn't matter. In the case of calcium fluoride, the KSP for it is actually 4.0 times 10 to the minus 11 at 25 degrees Celsius. That's a pretty small number, which tells us that calcium fluoride is not very soluble in water. So let's practice some of the math that you're going to do with this KSP. Let's take an easy example where we calculate KSP from a solubility. We have copper 1 bromide, and by the way, this example is also worked out in the textbook. All the examples that I work in this PowerPoint are in the textbook as well, so use your Zumdahl textbook. We have copper 1 bromide, measured solubility 2.0 times 10 to the minus 4 moles per liter at 25 Celsius. Find its KSP value. So your first step would be, let's write what dissolving copper 1 bromide looks like. So copper 1 is Cu plus 1, bromide is Br minus 1, so CuBr solid makes Cu plus 1 and Br minus 1. Step 2 would be, let's make an ice table. Notice I don't include the copper 1 bromide solid in the ice table, just the ions copper plus 1 and Br minus 1. They start at 0. They dissolve until they reach equilibrium, so they have a change of plus X and plus X. And so at equilibrium, the amount of copper plus 1 is algebraically called X, and Br minus 1 is also called X because they are in a 1-to-1 ratio. Step 2 would be to use the solubility to find the KSP. The solubility in this case would be X. There is a 1-to-1 ratio. For every mole of CuBr dissolved, 1 mole of copper plus 1 and 1 mole of Br minus 1 dissolve. So the X value is the solubility of copper 1 bromide solid. So in that case, just plugging in X into the KSP expression. KSP would be copper plus 1 times bromide minus 1, so that would be X squared. So we're looking at 2 times 10 to the minus 4 squared, or 4 times 10 to the minus 8. We omit units because we never use units with equilibrium constants. Here are a bunch of KSP values for a number of ionic compounds in water, to 108 x to the 5th. Here are a bunch of KSP values for a number of ionic compounds in water. So you can see that there are various values, and some are very, very tiny, meaning they're almost insoluble, and some are kind of partially soluble, and others are, really low solubilities. To 108 x to the fifth.
So here we have calculating the KSP from the solubility problem 2. We're supposed to calculate the KSP value for bismuth sulfide, which has a solubility of 1 times 10 minus 15 moles per liter at 25 Celsius. So we write the solubility equilibrium expression, Bi2S3 solid makes 2Bi plus 3S minus 2. We set up our ice table. Bismuth and sulfide start out as 0. The change is plus 2x and plus 3x because of the coefficients. So equilibrium is going to be 2x and 3x. So the KSP is going to be the bismuth squared times the sulfide cubed, once again because of the coefficients. So it's 2x squared times 3x cubed. That all multiplies out to be 108x to the fifth. X is the solubility, so the KSP is 108 times 1 times 10 minus 15 to the fifth, or 1.1 times 10 to the minus 73. So you can see that when you have more than just 2 ions, it gets a little more complicated, but it's still doable. The KSP value for copper 2 iodate, CuIO3 taken twice, is 1.4 times 10 minus 7 at 25 Celsius. Find its solubility. Now here we see that we can go the other direction. It's always good to know how to do AP Chem problems both directions. So here we're going from the KSP to the solubility. We set up the solubility equilibrium expression, CuIO3 2, makes Cu plus 2IO3 minus. We do our ice table, 0, 0 plus x plus 2x, x and 2x, and the KSP is going to be 1.4 times 10 minus 7. And that's going to equal x times 2x quantity squared, which is 4x cubed. Solve for x because now we're trying to find the solubility, not find the KSP. So we set 1.4 times 10 minus 7 equal to 4x cubed. We divide both sides by 4. We take the cube root. We get x equal to 3.3 times 10 minus 3 moles per liter. This time we want to include the units because it's solubility, not KSP.
Because the relationship between the solubility and the KSP are different, and they're calculated differently. In this case, CUS has the larger KSP value, but the lower calculated solubility. Table 15.5 down below here has the calculated solubilities for these three based on their KSPs. And you can see that the one with the smallest KSP is actually more soluble, and the one with the largest KSP is actually less soluble.
So on this slide, we're trying to show that that depending on the number of ions, you can, in some cases, if you have the same number of ions, compare the KSP to the solubility. Case 1, all of them have 2 ions apiece, so they all have solubility equal to the square root of KSP. So the order of solubilities is the order of the size of the KSP. But when it splits into multiple different numbers of ions, CuS makes 2 ions, silver sulfide makes 3, bismuth sulfide makes 5. So based on the way we convert KSP to solubilities, you can get a different order than the order of the KSPs for the order of the solubilities.
Finally, we're going to look at the common ion effect. Now, so far, we've only talked about adding salts to pure water. But there are many cases where you're trying to dissolve a salt in a solution, and the solution may contain an ion that is one of the ions in the salt. In that case, we call it the common ion effect. A common ion, in other words, if an ion is already in the water that is common to the salt that you're trying to dissolve, you will find your salt will have lower solubility. So the common ion effect, the solubility of a salt in a solution containing a common ion is lower than it is in pure water. Silver chromate, for example, Ag2CrO4, one of the ions in silver chromate, of course, is going to be Ag+1. Now, in pure water, the solubility of silver chromate is 1.3 times 10⁻⁴ moles per liter, because the KSP of silver chromate is 9.0 times 10⁻12, and that equals 4x cubed, and you solve for x and you get 1.3 times 10⁻⁴. But what would be the solubility of silver chromate in a solution that was 0.100 molar silver nitrate? Well, silver nitrate dissolves to make Ag plus NO3 minus. Ag plus is a common ion to silver chromate. And because you make one silver ion for every silver nitrate, a 0.1 molar silver nitrate would have 0.1 mole per liter silver plus 1. So now that changes our ice table a little bit. We look at silver chromate and we say, okay, how much silver chromate is going to dissolve in this solution that has 0.1 molar silver plus 1 already? Well, we set up our ice table, and for the two silver plus 1s, we have to give an initial molarity of 0.1 molar. An initial molarity of chromate, of course, of 0. We do still shift to the right to reach equilibrium. Change in amount of silver is going to be plus 2x. The change in the amount of chromate is going to be plus x. So our equilibrium amount is going to be 0.10 plus 2x for silver and x for chromate. Now, once we set up our KSP expression, 9.0 times 10⁻12 will equal 0.100 plus 2x quantity squared times the x for the chromate. Now, this would be a very difficult cubic equation, except that because KSP is small, we can neglect the plus 2x because the 2x is going to be small in comparison to 0.100. It's going to be negligible. So we neglect the plus 2x, and now it configures into 9 times 10⁻12 times equals, 0.1 squared times x. Divide both sides by 0.1 squared, and we get x equals 9 times 10 to the minus 10. Now, indeed, that is very small in comparison to 0.100, and obviously passes the 5% rule. So 9.0 times 10⁻10 moles per liter is actually the number of moles per liter of silver chromate that dissolve. Now, I think you've noticed something. It doesn't matter how the ice table is set up, x is always the solubility.
So there's another example of solubility in common ions. We're trying to calculate the solubility of solid calcium fluoride, that same example from the beginning of this PowerPoint. KSP being 4 times 10⁻11 and we're trying to find its solubility in a 0.025 molar NaF solution. So our equilibrium expression, CaF2 makes Ca plus 2 plus 2F minus. Our ice table would be 0, and in this case 0.025 molar, not 0.05. This is not 0.025 molar calcium fluoride, it's 0.025 molar sodium fluoride. Sodium fluoride only has one F minus, so the fluoride starts out at 0.025 molar from the sodium fluoride. We have a plus x and a plus 2x, so our equilibrium is going to be x in 0.025 plus 2x. Set up our KSP expression, 4 times 10⁻11 equals x, calcium, times 0.025 plus 2x squared, fluoride. We're going to neglect the 2x again, just like in the previous example. So now we have 4 times 10⁻11 divided by 0.025 squared equals x, and x equals 6.4 times 10⁻8 moles per liter, the solubility. And in fact, it is negligible compared to 0.025. Should always double check that. pH and solubility. It turns out that there are many salts that are soluble in acid even though they're not soluble in water. So let's look at what's happening that lets acid dissolve things that water cannot, or that water only slightly dissolves. A good example of this would be magnesium hydroxide. This is the milk of magnesia that you take for stomach acid. Magnesium hydroxide solid makes Mg plus 2OH minus. Now the key here is the 2OH minus. 2OH minus reacts with acid. H plus and OH minus makes water. The K is 10 to the 14th, so that's going to go to completion. If you react H plus with OH minus, you remove OH minus from the right side of the equation. So Le Chatelier's principle would say that means we shift to the right and more of the solid dissolves. In other words, it becomes more soluble. So this is actually how you're able to safely drink the milk of magnesia, magnesium hydroxide. You're able to get it down your throat because it doesn't burn your esophagus on the way down, because it's not that basic, because it's not that soluble. You're mainly swallowing it as a solid, not as ions of OH minus that could react with the esophagus. However, once in the stomach, it reacts with stomach acid. The H plus reacts with the OH minus, it turns into water, more of the magnesium hydroxide dissolves, and eventually it's all dissolved. And it's all reacted, the OH minus with the acid, and it's fully neutralized OH minus with H plus. Now, OH minus is not the only ion that can react with H plus. There are many other ions that can do that, such as silver phosphate. The phosphate ion combines with H plus to make HPO4 minus 2. Phosphate minus 3 is a conjugate base. So in general, if and that means any silver phosphate added to acid will be more soluble in the acid. In general, if your anion is an effective base, so if the anion of your salt is an effective base, in other words, any of the conjugate bases we've talked about, fluoride, acetate, phosphate, sulfate, anything that can absorb H plus and turn into a conjugate acid, that means that adding acid to that will shift the equilibrium to the right and make it more soluble in acid than it is in pure water.
Okay, so finally, let's wrap this up by saying, let's start doing more practice problems. Between now and the AP test, I really encourage you to do a lot of practice problems. In the time that we're not together in class, contact me, email me. That's probably my preferred. But if you are desperate, give me a call or text me. I'm sitting at home like you are with not a lot to do except make PowerPoints to send out to you guys and to kind of push out some homework and some practice to you guys. So give me a call, give me a text, and I'll try to get back to you, and we can talk about it in person if you need to. I've also added a remind code for AP Chemistry. Hopefully that will help us also to stay in touch. But let's stay in touch. We all need the diversion here. Instead of watching TV and playing video games, let's work on AP Chemistry. That's a lot more fun, I think, right? So the rest of the time between now and the AP test, whether we're together or not, let's keep pushing to review and practice for the AP test. This week we're doing Chapter 18. Expect another video tomorrow. Expect another video on Wednesday. And Thursday, Friday, send me your back of the chapter practice multiple choice for the AP test, and I will send you a quiz that you can work on. Remember, nothing we do this week counts for grades in the grade book. It's possible next week they might start counting. We'll just have to see what we're told to do by the state and what we're told to do by Dr. Hall. But in the meantime, just practice. I've actually suggested some questions and problems from the back of the book that you can look at. Now, I would say on these, you should read them all. And if you read it and say, oh, I know that, then move on. If you read it and say, I'm not sure about that, then look back at my lecture, look back in the notes, look back at the textbook. And if you still can't figure it out, shoot me an email, shoot me a text, shoot me a remind question, and I'll try to address it. I might address it with you, or I might end up addressing it on if it's something that everybody I think needs to hear, I may address it on the next day's notes. Okay, these are the example problems I would suggest you at least look at, and if you feel like you know how to do them, go ahead and move on. However, I do want to stress, just watching me do stuff doesn't mean you know it. You need to try one yourself and make sure you get the answer you need to get, or the answer in the back of the book, before you are sure that you know how to do something. Okay? Please stay away from my sleeping hours, 9 to 5 a.m. If you want to text me at 5:30, that's fine, but just not after 9 p.m. So thanks very much, and you all stay safe.